Okay, great. Thanks, Mark. So again, my name is Brian, product manager with Phenomenex, and today we'll be going over the characterization of oligos by LCMS. Really a lot of challenges with oligos, whether you're dealing with thioate, stereoisomers, myriad process-related impurities. What's going to be the most paramount for characterization and quantitation of nucleic acid therapeutics are the nuances in mobile phase composition that can be impactful, not only for chromatographic performance and separation, but also for ESI efficiency if you are performing any characterization. And, you know, the talk today, not as cool as NMR, but hopefully something practical nonetheless. So as a primer of the presentation that I'll be giving, just an overview of oligochromatographic challenges, and of course the bulk of the presentation on method development and the considerations that one must have for oligo analysis by LCMS. And we, of course, all know these things, but because I like to make the joke of a primer on oligonucleotides, oligos are short DNA or RNA oligomers, typically 20 to 60 mer, manufactured by solid phase synthesis, and they, of course, bind in a complementary manner. There are different types of oligos depending on, of course, the application. Oligos can be either single-stranded, double-stranded. In the world of molecular biology, in the diagnostic world, dual label probes, these are common, especially in the world of COVID-19 with qPCR and such. But of course, today, the focus will be on the therapeutic platforms. So 2' MOE gapmers. This is, of course, Ionis's platform. Trinitary GalNAc, siRNA, which we saw a bit of. That's also common for liver targets. Also of interest, the aptamer, which is an oligo that interestingly binds to things in very similar ways that a protein might. Of course, something that's not listed here, but something in consideration would be those that are associated to single guide strands for CRISPR applications. Those are typically around 100 mer or so, and that's probably another discussion for another time, but again, something worth noting. So some discussions on the different modifications of oligos and really how they pertain to chromatography, really. The most critical of the modifications, of course, was mentioned before, is the non-bridging oxygen phosphodiester backbone, the sulfur group that's associated to that in the phosphorothioate. So the so-called PS chemistry, that really is to minimize the hydrolysis by endo and exonuclease, and that, of course, confers stability. It is important, of course, that it does lead to introductions in diastereomers. And as this has, of course, been reported a number of times, that's 2 to the N isomers, where N is the number of thioate linkages. And of course, more important in today's discussion is the introduction of those diastereomers will create some peak broadening by chromatographic separation. And this, of course, will compromise the chromatographic performance. And thus, when you're trying to identify some of those process-related impurities, it makes things very complicated, to say the least. Some other notable modifications are the sugar portion of the oligo, that 2' hydroxyl group, that can get replaced. And that is going to confer different physicochemical properties for the oligonucleotide. So that will, of course, affect their behavior chromatographically and present some further challenges. And that extends even into the constrained nucleotides, so bridge nucleic acid shown here, more commonly the lock nucleic acid. Some other modifications out of scope of today's discussion: peptide nucleic acids, PNAs, or phosphoramidate morpholino oligomers, or PMOs, morpholinos. Out of scope of today's discussion because you treat them a little bit differently. You essentially treat them like a peptide, but they do have similar process-related impurities and also create some similar types of challenges. They just, don't require ion pair and things like that. So a little bit, I would say, more straightforward in that regard. You all probably hear my son in the background. Welcome to 2021, everyone. So some other possible process-related impurities with all the different modifications and stuff that you have. There are a lot, and they get super complex. Of course, the addition of that sulfur, not only the diastereomers that introduces, they also are going to have a high potential for oxidation. So that's so-called PSPO impurity. Chromatographic separation of that impurity is possible, though, of course, it is challenging. It depends on a whole host of things, not the least of which is how many different thioations there are and where that oxidation actually occurs. Of course, all the other impurities as well, positional isomers related to the sugar residue, capping impurities due to the solid phase synthesis, depurination, of course, that can occur under even mildly acidic conditions. And this is not even mentioning the standard N-1 and N+1 impurities that one has to characterize for any solid phase synthesis. And there's also higher molecular weight impurities as well. So those are in consideration as well. And really, if you want a more comprehensive overview, there's a white paper by Daniel Capaldi and colleagues. So Daniel Capaldi out of Ionis really just put together a very extensive overview and suggested identification thresholds, etc. So I'm sure many of you have seen this white paper, but definitely something to refer to as you venture into the world of analytical methods development for oligos. And so the chromatographic challenges, and so, obviously oligos, very challenging to work with. Before we start to talk about method optimization by ion pair reversed phase, just a brief primer on reverse phase LC itself. And so this involves the partitioning of an analyte between the mobile phase and stationary phase with interactions typically driven by hydrophobic mechanisms. That's the reason why we use C18s for that methylene selectivity. And of course, this is very straightforward with a hydrophobic compound, but with oligonucleotides, of course, you have something that is relatively hydrophilic, and it is also negatively charged. And with any silica-based material, at least, you're going to have some acidic silanols. Those can have a propensity to electrostatically repulse an oligo, which already does not want to retain onto that hydrophobic C18 or alkyl chain type of stationary phase. So really, in short, reverse phase media simply does not retain oligos under normal conditions. And so, of course, maybe you could try helic chromatography, and certainly Pat Limbach at University of Cincinnati would be a strong advocate of that. But the more common approach to this is of course, ion pair reverse phase. And so the standard way to do this is using alkyl amines. The most common one, of course, is triethylamine, TEA. Some others worth noting, and one that Michael Bartlett's lab, who is actually presenting after me, and I really don't know what I can say outside of what Michael Bartlett has said, but I'm going to try nonetheless. But either way, his lab looked extensively at the different number of ion pair and hexafluoro in all the perfluorinated alcohols that are associated with the reversed phase mechanism. But outside of TEA, you can look at diisopropylethylamine, DIEA, dimethylcyclohexylamine, which I've seen quite a bit in the literature as well. But there's others, hexylamine, that's one that we actually commonly use in the lab. But those tend to improve the chromatographic separation pretty considerably, and we've at least for single-stranded modalities typically use the more hydrophobic ones for a little bit better performance, not only from a chromatography perspective, but also from a mass spec perspective as well. So let's move on into method development and really just look at the different method development parameters that one could adjust and modify in order to get the best out of their analytical HPLC separation. And so an overview of what that would look like. And so, oftentimes I think, and as a column vendor, we can certainly appreciate different labs just wanting to try different columns, but sometimes you can get a lot more out of your analytical methods simply by making adjustments. And really it is with the mobile phase itself. And so I think a lot of analytical chemists tend to gravitate more towards, in the world of small molecule reversed phase, 0.1% formic acid, or if you're a protein person such as myself, 0.1% TFA. That seems to be a common thing to do. And of course, in the world of oligos, we simply can't do that. Not only because oligos won't retain without some ion pair, but of course, oligos under those acidic conditions probably not going to fare too well from a stability standpoint. And so, at least for today's presentation, we'll mainly focus on some modulation to the mobile phase, but we'll also touch on temperature and gradient, slope, and flow rate, which are two interrelated method parameters that one can adjust to get the most out of their separation. So I don't really talk about hexafluoroisopropanol too much, but HFIP is typically the acidic modifier that's used. It is very critical to the ESI droplet formation for mass spec characterization. But even outside of that, even for standard LCUV applications, it tends to perform better than, let's say triethylammonium acetate, which is, at least from a purification standpoint, certainly a lot more common of a buffer system to use. HFIP just tends to work better from a separation standpoint, lets your ion pair essentially work better. And so that's the more common one to use. However, oftentimes what's, and this, a lot of this is from the work that Martin Gallart Waters did in the mid 2000s, was using a lot more HFIP to basically get oligos to retain even better than, some of the older column technologies out there, wherein we were trying to get the most out of the retention. And so 400 millimolar HFIP was actually pretty common concentration. Entirely too much HFIP, and you see now more applications where 100 millimolar is more common. But what we've seen in our method development and working with various different types of oligos is even less HFIP than that tends to work better. And so if we look here at this BNA titrating concentrations now from 100 millimolar to 12.5 millimolar, you are definitely seeing that improved separation, and your impurity profile and your percent purities are actually slightly different by going down by that amount. And so, it's one thing to say that, you are improving the chromatography, but it's another thing to actually look at some of the gains that we see from a mass spec perspective. And so, again, looking at 100 millimolar, kind of the mainstay for HFIP concentration, compared to 12.5 millimolar here, seems to be about a 20 to 30% difference in sensitivity. And really that extra sensitivity in the later eluting peak is actually shown here. And so because of that extra sensitivity, we get even better characterization as well. And so, something of note with the decreased amount of HFIP, there is a slight decrease in retention. Intuitively, one might think that decrease in retention, maybe the ESI isn't quite as good, but again, we see that that increase in sensitivity, and it's almost irrespective of the different type of oligo and, heck, even the type of column that you're using. Simply decreasing that HFIP from that 100 millimolar leads to some very, very good results from an ESI sensitivity standpoint. Now, of course, one worry is when you decrease HFIP, mobile phase stability might be a concern. And so, in looking at the triplicate injections here, at least intra-assay precision or repeatability seems to be decent. So we look at the tick, and the tick overlays pretty nicely here. And also looking at the charge envelope and the stability of that, that seems to look pretty good as well. It is interesting to note, though, if you zoom into, let's say the -9 overlay here of the spectra, you can see a slight decrease in signal, but at least, one can expect at least your intra-assay precision to be reasonably good. Otherwise, again, retention times still tend to be spot on, and even decreasing that HFIP shouldn't adversely affect the method robustness too much. Although it is something to consider. If robustness is of the utmost concern, you may, sensitivity is not as much of an issue, and maybe your separation is good enough. Increasing the HFIP as well as the ion pair, that may, of course, give you a little bit better mobile phase stability. So in comparing the differences in ion pair concentration, so one of the things, of course, is if you decrease HFIP, ultimately what that's going to do is decrease the overall retention of the oligo that you're looking at, wherein now you can really start to expand your experimental design for how much alkylamine you're actually adding. And of course, if you add a little bit more, that's going to, in general, yield a more favorable impurity profile. So here comparing 4 millimolar versus 16 millimolar TEA for this 21 mer single-stranded DNA. 16 millimolar, that's quite high. You might be hesitant to use that amount, but ultimately you are going to get a much better separation there. And if separation is of a concern, the higher amounts of alkylamine are certainly going to help. Of course, TEA is one alkylamine, but there are all the other variations that I alluded to as well. And so, again, less HFIP. Now we can start to use a little bit more of the esoteric, let's say, alkylamines, and really the more hydrophobic ones. So diisopropyl ethylamine, DIEA, seems to be quite common. And actually, if you look at 4 millimolar versus 1 millimolar DIEA, you actually get even more retention with that slightly decreased amount of DIEA. And, if your lab is averse to using higher concentrations of alkylamine, if you have a shared resource in your high resolution mass spec, for example, that's certainly an attractive option. Otherwise, another thing that you can do is look at things like dimethylcyclohexylamine, DMCHA, and hexylamine, the one that we tend to use pretty commonly, using even smaller concentrations. Those 1 millimolar, you actually get reasonably good results. However, that higher amount of ion pair is still probably going to improve. You're probably still going to get better spectral quality data, and that really is twofold. Not only do you you tend to get an improvement in sensitivity, but that improvement in separation with the higher amounts of ion pair can actually start to separate out some impurities. And in this particular instance, looking at 2 millimolar versus 10 millimolar HA with a 2' MOE gapmer, we can actually see the early eluting impurity separating out much better on that 10 millimolar, basically getting baseline separation and yielding much better spectra because there isn't the spectral overlap due to the coelution that's observed with the lower concentration of HA. And so the N-2 shortmer impurities are actually separated out much better. There is also a nominal effect in the decrease of adduct formation. So, sodium and potassium adduct form pretty readily, and as much as we try to passivate systems and make sure to clean glassware, et cetera, you're going to likely see them within your spectra. And so, adding a little bit more ion pair tends to minimize that formation during the ESI, so that's something to also consider as well. Either way, overall, for the recommendation for mobile phases, keep your HFIP relatively low, so 12.5 to 25 millimolar HFIP, higher concentrations. That tends to do better for both ESI sensitivity as well as separation. And gravitating more towards the hydrophobic ones, at least for the single-stranded modalities, things like hexylamine, DMCHA, DIEA, et cetera. And so the other thing to take a look at also, and something I think is interesting as well, is looking at the changes in the charge envelope based upon the types of alkylamine that you're using. And so the data is not shown here, but if you have triethylamine and you modulate the concentration of that, you're really not going to change the charge envelope. It's more or less going to remain the same. However, as you start to look at different alkylamines, your charge envelope now changes. And of course, this is important because if you are, let's say you're trying to quant by MRM, or you're trying to minimize some of the interferences that one might see in a sample, just have them a more specific method here. Changing the alkylamine that one is using, that actually might yield some interesting results. So something that we're exploring further. I will say this, that it tends to be, it seems to be oligo specific. That is, in this example here, HA does show some of the lower charge states, a higher M over Z's, but that may be different for another oligo wherein you're actually seeing more of the higher charge states. So further work that needs to be explored, but I think that's something that's interesting nonetheless. Now, I would definitely be remiss if I didn't mention the nuances that are associated with duplex oligos, so siRNAs or any double-stranded type of modality here. And, this is using, we do have the decreased amount of HFIP, but, we're just using the standard triethylamine at 4 millimolar and a reasonably good separation of sense and anti-sense strand. However, as we start to look into other, let's say alkylamines here, you get some really interesting chromatography. their trace kind of looks like Batman. And it's this weird thing that happens with the duplex RNAs that we've seen is that as we start to look at whether that's HA or DMCHA, just some errant chromatographic behavior that isn't repeatable. That's the other issue with this as well, is that the chromatography can change from injection to injection. And so at least with duplex RNAs, so in working with siRNAs, triethylamine, at least with the methods that we've worked with, seems to work the best. And so, separation aside, if the intent is to separate sense and antisense from each other, certainly using TEA or some of these shorter alkylamines tends to fare better than something like HA or DMCHA. And, we did get a bit ahead of ourselves here talking about duplexes. We should probably also talk about melting temperature. So, the temperature by which that annealed oligo melts, it dissociates. And so, I think it's a very common practice for folks that are doing any analytical LC for oligos to just run as hot as possible. So, just run at 60, 70, even 80 degrees just to really push the limits of the silica. And so, with siRNAs and with duplexes, that definitely is going to be impactful. And so, based upon the theoretical melting temperature here as calculated by Oligo Analyzer from IDT, you can see as you're running, hotter and sort of closer to where that or further away, I should say, from that melting temperature, that is going to improve in the separation. Now, of course, other chromatographic levers that we could pull, whether that's adjusting the gradient slope or even decreasing HFIP, I guess in this example, that might be able to pull those two apart. But fundamentally, one must run at a higher temperature to see that dissociation. So duplexes, of course, you're going to want to run further away from that melting temp. Let's call it, upwards of 10 to 15 degrees higher than the theoretical melting temp. However, with single-stranded oligos, you may not need to run as hot as possible. And so, if you're looking at, so this is just a 20 monomer oligo with a amino C12 basically at the 5' end. Let's replicate a oligo that has been conjugated. And so, if you were to take this and essentially run it, incrementally higher temperatures, one can see, of course, we see a decrease in retention time. We do expect that. However, when we look at that impurity profile, there really isn't much of a difference. And so, one can try to look at the sequence for that oligo and, look at the GC content, for example, and say, okay, well, this GC content is pretty high. Maybe I should run it at a higher temperature as possible. But sometimes that actually doesn't really play out. And it may be oligo-specific in the intermolecular interactions, which may be compromising chromatographic performance. Either way, sort of the heuristic of running at the highest temperature as possible, that may not be necessary for your oligo of interest if it's a single-stranded modality. And, as much as Phenomenex, we appreciate everyone buying all of the columns, do what's practical and what's going to be the most robust and such. And you're really stressing your column running the hotter and hotter temperatures. So if you can get away with even 45 degrees for your separation, that will overall just improve the column lifetime pretty considerably. So finally, we'll just discuss really briefly the effect that flow rate has. And so flow rate is definitely, I think, an underutilized tool in the world of large molecule, or maybe, let's say, an improperly used tool. And so really with the advent of core cell particles with sub-2 micron particles, essentially we can run as high a flow rate as possible, as basically as much as our system will let us run. And so the reason why you would do that is, in the world of large molecule, when you run at higher linear velocities or higher flow rates, while essentially keeping the gradient program the same, this shallows out the gradient slope. So by gradient slope, we mean that change in percent organic or percent B per column volume. And so, again, because you're not losing out in efficiency with sub-2 micron and core shell particles as you run at those higher flow rates, you can really start to shallow out gradient slopes, really low, so lower than 0.5% B per column volume, even in some instances, in order to just maximize that separation. And so in this example, we have 0.3 mil per minute versus 0.5 mil per minute. Of course, at the faster flow rate, 0.7% B per column volume, probably even go lower than that. either way, you are, separating out this pre-peak that didn't show up with the lower linear velocity. And so, I see this problem, especially with folks that are working with proteins, but even oligos is one of the ways that you try to improve the separation is instead of increasing the flow rate, you just take that same gradient program. Instead of 14 minutes, now it's 28 minutes, which could work. And you've shallowed out the gradient slope in a certain regard, but now you have twice as long a method. There may be some question about stability of that oligo, especially if you're running at higher temperatures and things of that nature. So, just practicality's sake, it's, who wants to run a 28-minute method if you can run a 14 method, right? A 14-minute method. So, in a lot of ways, using flow rate as a way to shallow out the gradient slope, especially with these UHPLC type of particles. And if you have a system that can accommodate for these higher back pressures, running at that higher flow rate is certainly going to be the more practical approach. And so, just one final example, looking at a 2' MOE gapmer here. And so really, if you're working with a 2' MOE gapmer, these things, because of their diastereomers, fully thioated, can have pretty broad peaks. And so you need every bit of separation power that you can handle. And in this particular instance, cranking a flow rate going from 0.3 to 0.5 mil per minute does yield significantly better separation of earlier eluting and later eluting impurities. So hopefully I didn't go too fast. I was trying to pick up on some time here, but so as a summary, oligos pose many analytical challenges, often addressed through mobile phase additives for LC analysis. So modulating things like the different types of alkylamine that you're using, as well as even your concentration of perfluorinated alcohol, that can improve chromatographic performance, as well as increase mass spec sensitivity. Each one of these should be explored. And it's going to be oligo specific, especially if you are dealing with, let's say, a duplex oligo that's going to take a different approach chromatographically than one would do with a single-stranded modality. And then finally, simple method adjustments. So things like temperature and flow rate, very easy things to do, literally a couple of clicks on your mouse to your method. Those can actually lead to some incremental improvements, but should be explored, especially something like temperature for a single-stranded oligo, going to be different for a duplex.